Hello and welcome to ACSC Academy. This is our NIMSET series in which we are currently dealing with the topic of quadratic equations. Till now, in the previous videos, we have already covered the conceptual and theoretical part about this chapter, and now it's time for problem solving. We will be having a look at a number of problems that will enhance our conceptual understanding even more, and then we will be dealing with the problems that will help us improve our speed and accuracy from the exam point of view. So this is the foundation, this is the first topic we have taken from the maths part, so that it will be helpful in the future chapters that will be coming up if we go in that particular order, following the algebra first, then calculus, and then coordinate that particular way. So this topic is going to be a foundation, very useful for the upcoming chapters as well as exam point of view. So it's very important to get a good understanding about it by solving multiple problems, and then we'll also be having a look at the PYQs. So let's gear up and get started. So before starting today's set of problems, let us first have a look at this particular problem which was given as homework in the previous video. We hope that you all might have definitely given it a try, and you might also have been able to prove it successfully. So let's go through it quickly. The question was that this was a quadratic equation that was given. It was having its roots as P and Q, and we needed to prove that the value of this particular expression is, as it is given over here, b square minus 2ac upon a square c square. So this was a prove that type of question. Definitely such questions are not asked in the exam. It will be MCQ based, but when you are able to prove this particular problem, then based upon this we can definitely convert it into an MCQ type of question as well. They will say that this left hand side will be given and they will ask what is it equivalent to, and then this right hand expression will be given as one of the options for that. So you don't worry about it whether it is a proof that or MCQ type of question. The conversion is very easy, we don't need to worry about it. So it was an easy question. Let us quickly see how it can be approached. So given our quadratic equation with its roots as P and Q, first thing that comes to our mind is that sum and product of roots. So we'll quickly write P plus Q as minus B by A, PQ equal to C by A. Done. Now we'll stop over here. What next? Don't know. The expression given over here has AP plus B and AQ plus B. So here we do not see anything such as sum and product. So what is the use of these two? So we'll think for a little more time, and then the idea would have strike you that if P and Q are the roots of this particular expression, then we can definitely substitute them in that. It will satisfy, such as AB square plus BP plus C equal to 0 and AQ square plus BQ plus C equal to 0. Both of these would be holding true. So now if I look at it a bit further, I can see that from this first equation, if I take out P as common, then I will get AP plus B plus C equal to 0. So now this is where I got AP plus B. So from this particular equation, I can extract the value of AP plus B as minus C by P. We'll shift this on that side and then P will go in the denominator. So we get minus C by P from that. Similarly, dealing with the second equation, taking Q as common, we'll get AQ plus B plus C equal to 0, and from here we'll get AQ plus B equal to minus C by Q. So now we have values of both these denominators. So we'll now simply substitute them. So let's see, it is 1 by AP plus B the whole squared. So this thing will be reciprocated. We will get P squared by C squared plus from this side we will get Q squared by C squared, which is P squared plus Q squared by C squared. So this is what the result that we have got. But this is not exactly in the same format that we needed to prove. So now we will try to convert this into the desired format because this is in the terms of P and Q. But our right hand side is only in terms of A, B and C. So we need to get rid of this P square plus Q square. So now this is where the sum and products will come into the picture. Because what we actually need is the sum of squares of the roots. And that can be easily extracted using this particular formula that P plus Q the whole square will be P squared plus Q squared plus 2PQ. Now we already know the sum and the product. So we'll substitute these two and we will be able to extract the value of this sum of squares. So let us write down P plus Q as minus B by A, and square of that will give B squared by A squared minus of 2PQ, which is 2C by A. So this is the value of P squared plus Q squared that we wanted. We can further take the LCM and write that as P squared plus Q squared as B squared minus 2AC upon A squared. So now we will simply substitute this value over here. And as a result, what we'll get is this will become our numerator, and in the denominator there is already C squared. So combining these two, we will get B squared minus 2AC upon A squared C squared. This is the denominator and this is in the denominator of denominator. So that will again come in the original denominator. Now, if you're having confusion with this, then you might understand it using this example. We have already studied this in the fractions topic in the school, but let us revise it. If you have an equation of fraction a by b, and then in that denominator if we have something as c by d, then we know that it becomes a by b, and this lower one gets reciprocated as d by c. In the same way we did over here, we had this numerator over in this case, but in the denominator we had only one, only the numerator, denominator was not that, so we will assume that to be 1. Then when this particular rule is applied, that becomes a by b into 1 by c, which simply means that the entire thing comes to the denominator and the numerator remains unchanged. So that is what we did over here, and the result that we have got is b squared minus 2ac upon a square c square, same as the one which we needed to prove. So yes, it was very easy to prove this particular thing. Many of you might have already done this question. So now let us have a look at the next problem. This was also a homework question which was given in the previous video. Many of you might have been able to do it successfully. Let us see how it could be approached. This particular equation was given and we needed to prove that it is actually an identity. So now we have already learned what an identity is, that it will always satisfy, or it would be a quadratic which will have more than two roots. If I say that there is something like ax squared plus bx plus c equal to 0, a quadratic, and it is having three roots p, q and r, and provided that the coefficient is non-zero, definitely, otherwise it would cease to be a quadratic at the first place. So such a thing we saw that it turns out to be an identity, and then based upon the same we'll try to approach this particular problem as well. It will also help us to revise our concept of identity. So now looking at this, one thing you should be able to see that there is definitely no need to convert it into the form of a standard quadratic because it will become very dirty. We don't really need to do that. But just looking at it, we can see that we have x minus a, x minus b, then x minus b, x minus c. Like one term is missing here. X minus c was missing, x minus a is missing, x minus b is missing, and then accordingly the same thing has been repeated in the denominator. The one which was the c term was missing in this numerator, so they got c minus and c minus b in the denominator. So now looking at this, one thing we are sure that if I substitute x equal to a in this equation, what will I get? The first term will vanish because it is having x minus a as one of the terms. So that gives me 0. The second term, what will it give me? A minus b, a minus c upon a minus b, a minus c, which basically is 1. And then the third term will also give me 0 because there is x minus as one of the factors in it. So basically from the left hand side what I have got is just 1. It was 0 plus 1 plus 0, that is 1. Right hand side is already 1, which means x equal to a has satisfied the given equation. Now let us try to substitute x equal to b and see what happens. Now with x equal to b, the first term will give me 0 because x minus b is a factor. Second term will give me 0. The third term will give me 1 because numerator will become same as denominator, b minus c, b minus a. And right hand side is definitely 1, so x minus b has also satisfied. Let us check with x equal to c. First term will give me 1, second will give 0, third will give 0. Right hand side is already 1, which means this has also satisfied. What does this tell us? That x equal to a, b and c are all the roots of this quadratic equation. A, b and c, all the three values of x have satisfied this particular equation. If we call it to be quadratic, then it seems to have these three roots. So this is the concept of identity that we had studied. We encountered a quadratic which claims that it has three roots. So in such a case, it has to be an identity, otherwise it is not possible. An nth degree polynomial will always have n roots only. If it has more than that, then it becomes an identity and it will actually have infinite roots. That is what an identity is. We had seen this example, 0x squared plus 0x plus 0 equal to 0. If you consider such a quadratic, if you make the leading term as 0, then whatever value of x you put in it, it will get satisfied. We've also seen other examples of identity as well, and this was also one of them. A quadratic, a given equation that claims to have three roots. And actually they have not mentioned the word quadratic. Then why are we considering it to be 1? Because when you simplify it, when you write it in the standard format, it will have the highest power as 2 only, because you can see in all the numerators only 2 powers of x are being multiplied together. So it cannot have a degree greater than 2. Hence, if we convert it into the standard format, it will become a quadratic only. And in that case, being a quadratic, it seems to have three roots, which is what the violation is. And hence, this particular fact proves that given equation is actually an identity. So this was the solution for this particular problem. Now let us have a look at the today's set of problems. Now coming to first question for the day, let us see, we have been given a quadratic equation whose roots are said to be p and q, and we are asked to find out another equation whose roots will be p upon 1 plus p and q upon 1 plus q. Now this is such a simple thing. We have been doing this from past so many classes. We are pro in this. We will simply find out the sum of roots, product of roots, and then find out the new quadratic equation. That is so easy. Yes, it is definitely simple and you can do it by that approach, but here they have added an additional constraint that we need to use transformation of roots. So now definitely in the exam they are not coming to see which method are you using, but here just for practice and understanding, we are trying to solve this question by this particular method. And it will also help us to revise the concept of transformation of roots, because we have just a superficial understanding about it, and we don't know its true potential, that how helpful it can be for solving such a problem. Because there will be times and instances when finding out the sum and product will get very difficult. The equations will be very dirty. So in that case, this can come to our rescue. Let us see how. So before solving the problem, let us understand the concept of the transformation of roots. What does it exactly mean? So basically we have initially a quadratic given to us q1, which has two roots p and q, and we are asked to find out a new quadratic q2. Let us say its roots are p dash and q dash. So now this is what we call as a transformation. What actually happened is q1 got transformed into q2. How? Because we transform its root p into p dash and its root q into q dash. So basically when we convert p into p dash and q into q dash, then as a result of this, the quadratic q1 also gets transformed into a quadratic q2. Basically this means that we find out the q2, the new equation which will have the given roots. So this is what we mean by a transformation. You will be given initial quadratic. Using that you will find out its roots, and then you will be given two roots and you will be asked to find out a quadratic which has these two as its roots. That's what we do in such questions, right? So by doing transformation we can very easily find out this unknown thing, which is q2. So let us see how exactly does it happen. So talking about this particular question, we have our initial roots as p and q and our new roots, which means the roots of q2, which we are in general calling as p dash and q dash. They have been given to us as these: p by 1 plus p and q by 1 plus q. So we will convert p into p dash, q into q dash, and as a result we will get a new quadratic. That is what we need to find out. So now let us see how it is done. Here we have our original quadratic q1 as ax squared plus bx plus c equal to 0. Now p and q are its roots, which means if I substitute p in place of x, then it should satisfy the equation. What I mean is ab square plus bp plus c equal to 0 will also hold true, right? Okay, now using this thing, let us come to the new roots. Let us say that q2 is the new quadratic having its roots as p by 1 plus p, q by 1 plus q. Now what I will do is, in this quadratic q2, I am assuming the general root x, and if I substitute this p by 1 plus p as the value of x in q2, then it should definitely satisfy it. The same as we did in q1. In place of x, I substituted one of its roots, right? And then I got this. In the same way, in q2, if I substitute one of the roots in place of x, then it should satisfy q2, right? Yes. Now using this concept, what I'll do is I will simplify this thing. I will cross multiply it and I will write it as x plus xp equal to p. From this I will find out the value of p as x upon 1 minus x. You can simplify it and this is the value you will get for p. So now why did I find the value of p? What was the need of it? Can you think about it? Okay, alright, let's see. Now what we will be doing is we will use this particular value of p and we will substitute it over here. But why are we doing this? We'll understand shortly. For now, let us do it and see what is the result that we get out of it. So this is the value of p which I will be substituting over here. I'll get a times x by 1 minus x the whole square plus b times of x by 1 minus x plus c equal to 0. Now we have to simplify this thing. Let's make space for it. And the result which we will be getting after simplifying it will be q2. Yes, let's see how. So here we get ax squared upon 1 minus x the whole squared, or better, let us take this to the right hand side. It will become ax squared plus bx. I'm multiplying the entire equation, multiplying and dividing by 1 minus x the whole square. So that will give me this plus c times of 1 minus x the whole squared equal to 0. Right? Now you are definitely pro at doing such small simplifications. There's no need to explain. Then this will become ax squared plus bx minus bx squared plus c minus 2cx plus cx squared equal to 0. Standard format will be a plus c minus bx squared. These three terms are gone, plus b minus 2cx plus c equal to 0. This is what we have got. What we actually did is we wrote x equal to p upon 1 plus p, which is the root of the new quadratic q2, and then we substituted. We wrote down p in terms of x as p equal to x upon 1 minus x, and then we substituted this value of p back in q1 because p was its root, and as a result of this we have got this particular equation, and this is nothing but q2. If you don't believe me, let us also use our traditional method and verify the things. Now using the transformation of roots method, we have found out a quadratic q2, but we need to verify if it is correct or not. For that we will use the traditional way. We have this quadratic having roots p and q. We want another one which will have roots as these. So let us quickly find out the sum and the products and check it out. You are already aware of it, so we can go very fast. Here we get the sum as, taking the LCM, p plus 2pq plus q upon 1 plus p plus q plus pq. That is 2c minus b upon a minus b plus c. After simplifying, this is what you will be getting. You can verify for yourself. Similarly, the product of roots that we get is pq upon 1 plus p plus q plus pq, which then becomes c upon a minus b plus c. So yeah, we have got both sum and the product. We can now find out the quadratic q2. So using the sum and the products, the value of q2 that we will get is x squared minus sum of roots into x, 2c minus b upon a minus b plus c times x plus product c upon a minus b plus c equal to 0. This then becomes a minus b plus c x squared, taking minus out, b minus 2cx plus c equal to 0. Now, isn't it the same thing which we have got using the transformation of roots method? This is the same quadratic q2. Here we found that using the sum and the products. Here we could do it quickly because now we are habituated, we are used to this method. But there will be times when it will be very difficult to find out sum and the products. For example, if I say that You need to find out a new equation whose roots will be p cube minus plus p square minus 7p plus 4. Q raised to 4 minus 2q square plus 3q. So if I say find out a q2 whose roots are these. So now here, won't it be very difficult to find out sum and the product? Yes, it will be. So for some of these cases, we have another method called transformation of roots. But don't think that you can always use it. There are some restrictions which we'll be having a look at. For example, this one which we just saw, here you cannot apply the transformation of roots method as well. Why? We will see. So what you will basically do in such dirty problems? Here there will be some catch. There will be a trick. They will not expect you to apply the traditional sum and products method to such dirty roots. Okay, we will come to that problem later. First, back to the original one, we were discussing that yes, we have got the same Q2 from both the methods, transformation as well as traditional. But why did it happen? How does it work? So let us understand the why and how out of it. You can take a minute to think. It's not that difficult. Just think about how does it work. So are you done thinking? Did you came up with some idea? If yes, then let us see if what you were thinking is correct or not. Otherwise, you can take some more time to think and then come back to watch the explanation. So going with the basics, we had this q1 which was having roots as p and q. We wanted to find this q2 whose roots were already given as p dash and q dash. Now this p dash q dash can take any values. As in our question, we had p dash equal to 1 by 1 plus p, and same for q as well. So this was the problem. These green parts were known, the red part was unknown. That is what we needed to find out. So what did we actually do in the transformation of roots method is that we used two things. First, we said that if we substitute x equal to p dash in this q2, it should satisfy it, right? Definitely, because p dash is the root of q2, so it will satisfy it. Then using this fact, this is a fact that if we substitute p dash in q2, then it will satisfy it. So using this fact, we came up with this equation, which in our case was x equal to p upon, this was p upon 1 plus p. So we came up with this equation that if I substitute x by this thing, then it will satisfy q2. Then what did we do was we found out q in terms of x, and it came out to be this way, p equal to x upon 1 minus x. We simply converted x in terms of p into p in terms of x. This is what we got. Then what did we do in step 2? This was our step 1. Then in this step 2, what did we do was we used the same logic and applied it in q1. We said that we can substitute p in q1. Why so? Because p is the root of q1, right? So we can definitely substitute p in it. So then instead of directly substituting p over here, what did we do was we used this particular value of p. That is what we substituted here. Right? Can you recollect? This is what we just did in the previous slide. So that's what we did. In Q1, in place of P, we substituted its corresponding value in terms of X. And what this X is, This x is nothing but the root of q2, right? So using that x, whatever the equation that we have got, this thing, when we write it in the standard format, it will turn out to be q2 itself. Definitely, right? Now, are the things more clear? It should be, right? It makes sense. This b in terms of x, what was this x? X was the root of q2, right? So when we substitute that particular value of p in the original q1, then we will definitely get q2, right? Nothing new in it, no rocket science in it. Just simple logic. It's nothing more than that. This is the simple essence of transformation of fruits that is there. And maybe by using some more examples, there will be more clarity in the thought process that works behind this. So for now, the only thing you need to understand is that what we basically have to do is we have to write x equal to new root, the new root which you need to find. Okay, now one more doubt, that here why did we just use this p? We could also use q, right? Yes, we can also use q, and then in place of q you can substitute its corresponding value. That will also work. So what will you remember from this? The only thing, there are two steps that you need to follow. In step 1, you will write x equal to the new root. Then for that new root, you will find out the value in terms of x. And then what you will do is, you will substitute that in our original given q1 equation. The result which you will get after simplifying this will be nothing but q2 itself. That is how transformation of roots work. We will understand this with one more example. Let us have a look at this particular problem. Again, a quadratic is given whose roots are p and q, and we need to find another one, q2, having these as roots. We just discussed that there can be some dirty roots that can be given where we cannot apply the traditional sum and product of roots method. So here we will definitely not go with the traditional one. Can we use the transformation here that we have just learned? Will transformation of roots work over here? So let us see. The answer is no, it will not work. But why? Let us understand. So what did we learn? How is the transformation performed? We write x equal to new root. So x equal to p cube minus 3p squared plus 5p minus 2. Yes, definitely you can also use the next root, which is q. Anyone will work. And the next step was that we needed to find p as a function of x. Here, can you do that? Not possible, right? In previous question, there was a linear equation. So we could easily simplify it and we could write p as a function of x. But here it is such a dirty thing. It is a cubic equation in itself. There is no way we can easily find out p as a function of x. So here definitely we will also not go with this particular method. But this was one of the reasons why we are not going with transformation of roots. The second reason for this is also that the two roots given to us are not symmetric. What do we mean by symmetric roots? Such as in the previous problem, our roots were p by 1 plus p and q by 1 plus q. Now here, if I substitute, let us call this root 1 and root 2. In root 1, if I substitute q in place of p, what do I get? Q upon 1 plus q, right? And that is nothing but second root. Similarly, in second root, if I substitute p in place of q, I get p upon 1 plus p, which is first root. So this is what we call as the symmetric roots. We can interconvert them into each other by changing the variable. In this question, if we see, the roots are not symmetric. In this root 1, if I substitute q in place of p, then I get q cube minus 3q square plus 5q minus 2. This is not same as R2, right? So this is where we say that the roots are not symmetric. So whenever the roots are asymmetric or not symmetric, we cannot apply transformation of roots. The reason behind this is that we just told you that you can use either of the roots, either R1 or R2. Such as in the previous one, we told you that you can use this x equal to p upon 1 plus p, or you can also use x equal to q upon 1 plus q. It will not make any difference. But in this case, when your roots are asymmetric, it will make a difference. From this one, we have got p equal to x upon 1 minus x. From this, we would have gotten q equal to x upon 1 minus x. The same thing, right? Both of them are exactly the same. But when the roots are not symmetric, we will not get the same thing. And this is the reason we will not apply transformation of roots in this particular question. So what were the two reasons? First reason is that it will get dirty if we try to do so, because it's not easy to find out p as a function of x or even q as a function of x. And the second reason is that the roots are asymmetric. So because of these two reasons, in this particular question, we will not apply transformation of roots method as well. So now it all boils down to how to solve this particular problem. We cannot even apply the traditional way, and we cannot even apply the transformation of roots method. So now how to approach this problem? Can you think about some innovative way? You can just pause the video and think about it for some time, and then we will discuss. All right. So in the previous slide itself, we told you that when the given roots are seemingly very dirty, then there is definitely some trick behind it. So here let us try to see if there is something we can catch. The first root given is p cube minus 3p squared plus 5p minus q. The next one is this plus q plus 5. Let us try to simplify these a bit and see if gets converted into some more simpler format, familiar thing. Here if we take p squared common, then we will get p minus 3 plus 5p minus 2. So is it going to simplify the thing? So let us try taking p common. Then we will get p squared minus 3p plus 5 minus 2. Now from here can we get something? Looking at our original equation, and we know that p is its root, so we have one thing that p will satisfy it. So p squared minus 2p plus 3 equal to 0. This will hold true. So now using this, can we get something better? And let us write this, or let us convert this into p squared equal to 2p minus 3. And if we use this particular value of p square over here, then we will be able to reduce its degree by 1. So let us write this pq equal to 2p minus 3 minus 3p plus 5 minus 2. Then this becomes p minus p plus 2 minus 2. And that further simplifies to minus p squared plus 2p minus 2. Or we can write that in a better way as 2p minus 2 minus p squared. And we will once again substitute this value of p squared over here, and it will give 2p minus 2 minus of 2p minus 3. This gives 2p minus 2 minus 2p plus 3. Now there is a surprise that p is getting cancelled out and we are simply left with 1. So basically the given root this is nothing but 1. When you simplify it, it all boils down finally to just 1. P is cancelled out. It is independent of P actually. And in the same way, we will also try to simplify the second root. Maybe it will also boil down to a linear term or a constant term. We were basically trying to reduce the degree of this given root. And in the process of doing that, it boiled down to just a constant. We were expecting a linear or something, but instead we got a constant, and that is a good thing, right? And then in the same way, we will also work on the second root and try to simplify that even further. So let us try to do that as well. All right. So what we'll now be doing is, this is the second root that we have, q cube minus q squared plus q plus 5. We know that in the same way, after substituting q in the equation, we get q squared minus 2q plus 3 equal to 0. So we can substitute q squared with 2q minus 3. So here we will write this q cube as q times of q square, which is 2q minus 3, minus of q square, which is 2q minus 3 plus q plus 5. So this becomes 2q square minus 3q minus 2q plus 3 plus q plus 5. This is 2q squared minus 5q plus q plus 8. And then that becomes 2 times of, once again substituting, 2q minus 3 minus 4q plus 8, which is 4q minus 6 minus 4q plus 8. Once again the same thing happened, q got cancelled out and we got 2 as a result, which means this second root is nothing but a 2. So now things look very much simpler. We just need to find out a new quadratic equation whose roots will be 1 and 2. That is how simple this question has been brought down into. So now let us see. The question is done actually. There is nothing more that we need to do. We just want a quadratic whose roots are 1 and 2. So sum is 3, product is 2. Quadratic will be x squared minus 3x plus 2 equal to 0. Done. This is how simple it was, which was seemingly looking very difficult. If you had started to find out the sum and the product of these dirty roots, then you might have never reached to the solution. So the trick here was that you need to simplify whatever looks seemingly big and complex. It boils down, it gets simplified into something very simple. So that is what we need to do in such problems. Now this is the next question that we have. It has been told that this particular polynomial is a factor of another polynomial. Let us call this as P1 and this as P2. So P1 is a factor of P2, and using this information we need to find out what are the values of the unknowns M and N which are present in P2. So now from this, what essence do we get? That there will be an application of a factor theorem or a remainder theorem in this. And in those, what did we used to do? It was that we will write the given P2, that is x4, x raised to 4 minus mx squared plus n, as the given P1, which is x squared minus 3x plus 2 into some other polynomial, right? And there will be some remainder as a result. This is what we used to do in the earlier problems. We used to write dividend equal to divisor into quotient plus remainder. That is the exact same thing we are trying to replicate over here. So okay, we are done with this. And now what did we try to do was, we will estimate what will be the degree of this remainder. The given P1 and this given P2, what are the degrees that they have? P1 has a degree 4 and P2 has a degree 2. So using this, we will say that the degree of the remainder will be less than the degree of dividend, which means if this is a biquadratic, the degree of remainder will be less than or equal to, not even equality does not hold over, it will definitely be less than 4. So the remainder can be a cubic equation. So we can assume it to be something like ax cube plus bx squared plus cx plus d. This is what an assumption that we can make. And then what we'll do is we will try to substitute some of the some or all of the roots of this particular P2 so that the middle term will vanish out, and as a result we will be able to establish some relation between this P1 and this remainder. So hope you recollect the problems that we have seen earlier. Using the same thing here, what we'll do is first we'll find out the roots of P2, which here it is easy to see that the roots are 1 and 2. So we will substitute them. First, x equal to 1, that will give us 1 minus m plus n, equivalent to the entire middle term will vanish out, and here we will get a plus b plus c plus d. Next, if we substitute x equal to 2, from there we will get 2 raised to 4, which is 16 minus 4m plus n. That is equivalent to, substituting 2 over here, it will be 8a plus 4b plus 2c plus d. So this is what we have been able to achieve. Now what to do next? How can we actually find out what are the values of m and n? Let us think about it. Could you find out the catch which was there in this? All right. Maybe some of you might have been able to find out. Let us see. It has been told that P1 is a factor of P2, right? Let us read this language more properly, just highlighting this thing. P1 is a factor of P2, which means P2 divides P1. What does that imply? Can you think about it? P1 is a factor of P2, P2 divides Q1. What does that imply? Simply that the remainder will be 0. There will be no remainder left out. Then only we will say that it is a factor, right? Which means whatever we have done over here, these A, B, C, D, they all will be simply 0. And as a result, we have got two simultaneous equations in terms of m and n, which is 1 minus m plus n equal to 0, 16 minus 4m plus n equal to 0. Now we can solve these two simultaneous equations. We can substitute m equal to 1 plus n, that will give 16 minus 4 1 plus n equal to 0, 16 minus 4 minus 3n equal to 0, so we get 3n equal to 12, n equal to 4, m equal to 3. This is how this problem was to be done. There was actually no necessity of generalizing this remainder and writing it as a cubic equation and then substituting. We should have understood by the language itself that if it is saying a factor, then no remainder should be left out. Then proceeding in the same way, we can find out the values of m and n as 3 and 4 respectively. So this is how this particular problem could be solved. Now let us take some more examples and understand how this transformation of roots actually works, so that you will be in a better position to solve the problems. Let us consider this particular equation, ax squared plus bx plus c equal to 0, p and q be its roots. And now we need to find out new equations First, let us take three examples. First one, whose roots will be p minus 1 and q minus 1. Second, p squared and q squared. Third, 2p minus 3 and 3q minus 3. Well, 2q minus 3 it was. And then in the fourth one, we will consider 4p minus 7 and 2p minus 2q minus 8. So these are the four problems in which we'll be trying to apply the transformation of roots. For the first one, we now already know the method, so we can move a bit fast. We will substitute x equal to p minus 1. Then we will find out p in terms of x. That will become p equal to x plus 1. And we will substitute this value of p in the original q1. So that will be a times of x plus 1 the whole squared plus b times of x plus 1 plus c equal to 0. Then we will simplify this, and as a result whatever we get, that will be our q2. You can verify this yourself using the traditional way. That's what we needed to done over here. We could also have used q over here, so x equal to q minus 1. That would have given us q equal to x plus 1, and the result would have been exactly the same. So we can use both because the roots are symmetric. Then similarly for the second one, we will write x equal to p square or x equal to q square. As a result, we will get p equal to root x, q equal to root x. Now here there will be issue of plus and minus, what sign you need to take. So for this you will verify for yourself that taking which sign are you getting the required result. It is quite simple, but it will be better for understanding if you check it out yourself. Then we'll simply substitute these values of p or q in the original equation, and as a result we will get a root x squared plus b root x plus c equal to 0, something like that. You'll verify and check if it works or not. What is the actual issue with it? Then for the third one, we'll also do the same thing. They are the linear equations. So it will be easy to find out the values as a function of x. When it becomes quadratic and higher powers, then it is difficult. So here again, we'll write x equal to 2p minus 3 or 2q minus 3. As a result, we will get 2p equal to x plus 3 or p equal to x plus 3 by 2. Then we will substitute this value of p in our q1 and simplify that, as a result of which we will get q2. And again you will verify this using the traditional way if the q2 which you have got here is correct or not. So now third one is also done. Coming to the last example, we can write x equal to either 4p minus 7 or we can write x equal to 2q minus 8. From this one we will get p equal to x plus 7 by 4. From here we'll get q equal to x plus 8 by 2. We'll substitute this p in q1. We will also substitute this q in q1, and as a result of this we will get two different potential answers for the new quadratic q2. But which of them will be correct, or if any, that also you will check. And the reason this is happening here, there is a difference between the two, is that the given roots are not symmetric. We have already seen what the symmetric roots are. Here if I substitute q in place of p, I do not get the second root. Similarly for the second, I don't get the first root. So these roots are not symmetric. So in such cases we do not apply the transformation of roots method, and if we try to apply, the result is in front of you, that we will get different q2 from both the roots, and none of them may be correct. That you will be checking and verifying for yourself. That is the homework from this particular video. So the main highlight of this was learning the new technique called transformation of roots, and we also saw some of the different problems just based upon some product of roots and applying some tricks. How can difficult looking problems can be solved in a simpler way? That is what we tried to see in this thing. So in the next video also we will be coming up with another set of lots of interesting problems, and we'll be also entering into the PYQs. So that will be very much helpful for you from the exam point of view as well. Now, after getting all this conceptual clarity, you will be in a better position to be able to quickly solve the problems with more accuracy. And you need to keep practicing because you are having reference books with you, or you can find many questions online available in different websites for free. You can practice a lot of problems because only practicing is the key for acing this exam. By just getting the clarity, by just learning the concepts, you may not be able to do the same or replicate the same thing in the exam, because practice is must, that can never be avoided at any cost. So here we are practicing, we are learning new type of problems, and at your end it's your duty to also take some efforts from your side and solve as many problems as you can. You can take tests and you can keep evaluating your performance. That is how you will be acing this exam. So that's it for this video. We'll see you in the next part. Till then, keep practicing.